Okay, this is a solution for Stevenson book. It's chapter 4 supplement here, quantifying reliability. I think that's the problem. We're going to switch over. We'll take double check on this, but I think it's problem 4s.5, if I'm not mistaken here. A little bit of clarification on this. Okay. I would expect that you have read this part of the book here. What are we on? Page 175, approximately 175 here. Okay. And what we're talking about here is when we have chain probabilities. Okay, so the example here is there's a lamp with a 90% chance of working, and then another one that's downstream from it at 80%. And what happens is the overall likelihood of these two lamps working is zero point 0.9 times zero point 0.8. Okay, and then the other part of this, again, I'm just assuming that you've read this. Okay, so go through this a bit is what happens if one system, one lamp is a backup to the other. Okay, so let's switch over the problem. Read particularly this area in here, this example. That's rule 2 and the example come into play here for this problem. So I'm going to flip over to Excel. Okay, so this was sent to me by a student because this came up as a question. So these are screen grabs of the students, what they were working on here. Control Z. Okay, and so there was 3 screenshots. Problem 4 supplement dash 5. Guidance system of a ship is controlled by a computer, has 3 major modules. In order for the computer to function properly, all 3 modules must function. 2 of the modules have reliabilities of 0.97 and the other has 99. What's the reliability the of the system? Well, since the answer is kind of sitting there, let's work on this. All right, let's punch it in. I'm going to go a little bit long form on this. So we have a ship, okay, and system A, ship sys A, ship sys B, ship sys C. Okay, so we had a 0.97, 0.97, 0.98. Okay, there we go. Is that right? No, 9. It's 0.9. Okay. Okay, so since these are chained, all of these modules must function. So that would just be the probability of each of these multiplied together. So overall ship sys all of these, okay, let's say that all the systems working, it's just going to be equal to 1 times the next times the next. Okay, so this is where we get this number, and it looks like our student got it right. Okay, so the next one is a backup computer identical to the one being used will be installed to improve overall reliability, assuming the new computer automatically, where'd it go? Assuming the new computer automatically functions if the main one fails, determine the resulting reliability. Okay, so this is the situation where we have alternate paths. One kicks out. It would go something like this, right? Okay. So if one fails, then the loop would go to plan B, and plan B would kick in. All right. And the way that we look at that is you can take one system or you can take the other because they make them equals in this problem here. Okay. And so the way that that works is you take the probability of any one failing, which will be this 9.9315. It looks like the answer wanted to be 4 digits there. Okay, so it's the probability of that, the first one. So it's going to be prob of working of the first one, prob of working of the first one, okay, plus the probability of it failing. So it's 1 minus the prob that it was working, okay? It's the complement of that. I have to get this out of the way here. Star, notice the order of operations here, star, or multiplied times the prob of the second system. I'll put B down here, prob of B, second alternate system, or backup. We'll call B for backup, okay? All right, so all we need to do is it's going to increase the probability from where it was by the failure rate times the other one working, and they had equal behaviors here. So okay, so we're going to do ship shop ship backup. All right, so the ship backup, I'm going to just punch this thing in here. So it's going to be equal to the probability of the first one plus 1 minus the probability times the probability of the other, which happens to be equal to the first, okay, for this problem. All right, we hit enter, and it's 99.53 probability. I shouldn't be giving you the answers to this, but you should understand it. And then once you do understand, once you see it, then you can understand it. Okay, so I think those two are fairly well understood, understandable, comprehensible, right? That one and that one. It's the third one, just a little bit. You just have to think about parallel versus serial lineup of the problems, and it's similar to the first, but there's whoops, wrong pen. Similar to the first, but this is if it's fine. If it's fine, if the first system's working, fine. It's just okay, right? So that's okay. And what we have to do is the other one. Now we put a switch on the other one. Okay, so it's a little bit different than the first one, and the switch has probability of 0.98. Yeah, 0.98. Okay, so now we have another serial kind of the switch. By the way, the switch can be considered as a system, a little micro, tiny, very simple. But I worked on military radios, and switches and connectors are the bane of electronics, especially in defense operations. Okay, we had a special connector that had to be made. I had about 27 spring-loaded connectors in there, and that was as much cost in the system as it was for my entire computer circuit board and all the things that go on there and software and everything. This was a very expensive piece. We're measuring one of these connectors in the thousands of dollars here, just one connector. Okay, just to give you an idea, right? Try to make it a little bit more real here. Okay, so we just have to put the 0.98 into the equation that we just had. Okay, and so where that pops up is, I'm going to simplify it here. I'll use a different color. Okay, so this is for the third part. I've never used this color. Let's see what it looks like. Oh, that's gorgeous. I guess it's orange. Okay, times the probability of the switch, which was 0.98. Remember how we multiplied all three of these items had to work? Well, both of these items have to work. The probability of that secondary backup system times 0.98 with the switch attached to it. Okay, so it's really not that bad. Let's do this again. Ship. What do we call it? Back with a switch. Okay, something like that. All right. So we're just going to punch out the same equation again. We're going to say that's the probability of it working plus, now we need some parentheses here, 1 minus the probability of it working, or the probability that it will fail, right? Times, don't really need the parens, but it helps to show what's going on here, times the probability. Again, the backup system had the same probability as the primary system did, but now we're multiplying it by, and I forgot, I don't want to just put in 0.98, so I'm going to use this cell up here and come back to it. We're going to get a 0 out of this. Make sure you have enough parentheses there, or else you get yelled at. Okay. Okay, so I'm going to put in my switch up here. We'll fix the equation. It'll come out right. Switch probability is 0.98. Am I right on that? Yes, it is. Okay, and we come out with, it had been 0, and that's why nothing happened. But when we actually punched the number up here, and we used the cell, all right, we came up with, it comes back up to something like 99.40. It dropped a little bit. You're out in the thousands there.